All right. Wait, my screen is shared, right? You guys can see these slides. Okay. Well, happy Monday, everybody, and welcome to class. And I hope you guys are doing well. So, we got the notification that we will be online for the entire month of January, at least, and hopefully that will be it, and then we can go back in person. But one thing I was thinking, and I did this last year, when we were like online for a very long time. And this was inspired by Dinner with Strangers. I don't know if you've ever participated in Dinner with Strangers. It's like a UCLA Alumni Association thing. And anyway, I highly recommend it, if it weren't for the pandemic. But anyway, I thought, so, because we're not going to be meeting in person for a while, one thing we're going to miss out on is just student interaction with your fellow classmates. And I don't know if you know who your classmates are. And this is one reason why I ask you guys to turn on your cameras, is so you can see who some of your classmates are. And so you see their faces on camera and things like that. And I think it helps build a little bit of a sense of community. And I appreciate those of you who have put who put profile pictures on your Zoom, and some of you are turning on your cameras now, which is great. But yeah, when you are able to see some of your classmates, I think there is a little bit of kind of, I don't know, community sense, right? Versus just seeing names and not having any idea who these people are. But so one thing I thought we could do is we could have dinner with classmates. And so this is completely optional, and I'll have like a sign up sheet. And if you want to, and basically what we'll do is like, we'll meet at like 7 o'clock, and we'll just, if you want, you can eat your dinner in front of your computer, and you can just have a chat with some of your classmates. And if that sounds like it could be fun, then sign up. And if that sounds totally awful and you don't want to do it, then don't sign up. No biggie. But if you want to meet who some of your classmates are, I'll have a sign up sheet, and probably what I'll do, depending on how many people sign up, I'll make like groups of 8 people or so, and we'll have like a short meeting of around maybe like 1 hour, eat, chat, and that will be that. And you give you an opportunity to meet some of your classmates. So I'll post that up on Canvas or Campus Wire, and you can sign up if that sounds interesting. Up to you. Okay. All right. So anyway, let's get started on today's topic. Today's topic, we're going to just look at some programming basics, conditions, and loops. And I think a lot of this you are already familiar with, but we're going to just kind of formalize and give you a quick refresher here. Okay, so we have vectorized logical operators. Okay, so R has we have these operators. We have or and not and exclusive or. Okay, and basically you have a vector X, you have a vector Y, and it's vectorized, so it's going to do element-wise operations. And if one vector is shorter than the other, it will recycle so that it lines up. And basically, it's expecting logical vectors, true, false values. And if you give it a numeric value, these operators are going to coerce them into logical values. So anything that's other than 0 will get coerced to true, and zeros will get coerced to false. Yeah, other than missing values and stuff. Okay. On the other hand, we have the non-vectorized ones. So you have the double or, and you have the double and. Okay, and these ones are non-vector. And what they mean is that we're going to look at the vectors left to right, and we're only going to look at the first element of each vector. Okay, the longer this this non-vector is used inside if statements for control flow, because that's really the only time where you only want you want to limit yourself to just one value here. Okay, so here I've got x and I've got y. X is true, true, false, false. Y is false, true, false, true. And we'll go x or y. So x or y evaluates the or everywhere evaluates true, except in the case where we have false, false. The x and y, again, it's vectorized. So all of these things evaluate false, except in the case where it's true, true. All right, everywhere else you got or you got a false. With the non-vector or, it only looks at the first value, and this is going to be evaluated as true. With the double and, the non-vector and, it only looks at the first elements, and we get false. All right. So far, so good? All right. Thank you for nodding your head. Okay, so we've got logical vectors, logical operators. What happens when we plug in a missing value? What happens when we do true or missing? How is this? What is this going to evaluate to? So we have a missing value. So this missing value could end up being true. It could end up being false. What is this going to end up evaluating to? All right. So we got some people saying it's going to be true. Some people saying it's going to be NA. All right. This is going to evaluate to true. Okay. True or NA gets evaluated to true because whatever this missing value is, whether it's true or false, this statement is going to evaluate to true. Right? So true or missing, well, I don't care. I don't care what this missing value is. I just need one true and it's going to be true. Okay. But on the other hand, if we're doing a true and a missing value, we go, oh, now it matters, right? It matters, you know, both of these, right? It's kind of just like, you know, you're trying to make a decision. Okay. You know, should I buy a pair of tickets? You know, you got two people and, you know, I don't know, should I sign up for something? And you just want to make sure at least one of your friends can go. And then if one person says, yes, I can go, then you'll say, yeah, I'll sign up. Okay. It doesn't matter if, you know, the other person can make it or not, because we're going to sign up and we're going to go, because at least one of my friends, right? But then if the other thing is like, I need both of my friends to be yeses before I go in, you can get one confirmation and you go, okay, that's great. But you can't make a decision until the other person replies, right? So it's kind of like if you need the and, then it matters what your other friend says, right? So in that case, you don't know, right? So and then similarly with false or NA, so far one person has said no and you're not sure. This is like, I just need at least one person to say yes before I'm going to sign up for yes. So until that other person replies, it's going to be NA. Here you need both people to say yes, and one person has already said no, and so now it's going to be false. So these things can evaluate even with missing values. The exclusive or, one must be true and one must be false for it to be true. So true, false becomes true, true, true becomes false. False, false still stays false, but false, true is true. So the exclusive or is only one is true and the other must be false. Of course, anything with a missing there is going to evaluate to missing. Let me go ahead and give you your first view quiz answer for today. Today's first view quiz answer is the letter A. A as an apple. A as an apple. We've got any and we have all. Any is and all are like generalizations of or and for more than two values. Any is true if any of the values are true. All is true if only if all of the values are true. Okay. So here I've got U is true, true, true. Are any of these values true? Okay, so the responses here is give me the response for any applied to this vector U and give me the response for all applied to the vector U. So are any of the values true? Yes. Are all of the values true in this thing? Yeah. Here I've got V. True, true, false. Are any of the values true? Yes. Are all of the values true? No, false. Here I have false, false, false. Are any of the values true? That's false. Are all of the values true? That's also false. What do we do? What happens if we apply any or all to a null or a length 0 logical vector? Okay, so I've got a 0 length logical vector. Well, if you think about inserting a length 0 logical vector like a null into a vector that already exists, basically inserting a null or a length 0 vector will have no effect on that vector. Okay, so if you've got a vector and you try to insert something of length 0, it basically doesn't even affect the thing. So what should happen is if I run any on the combination of logical 0 and v, the result of this thing needs to be the same as any just applied to v by itself. Same idea, if I apply all on the combination of logical 0 and v, this should produce the same result as just all applied to v, all by itself. Does that kind of make sense what I'm trying to say here? So that if I include logical 0 along with some other vector, the result should just be whatever it was going to be for that other vector. So with that in mind, what does any logical 0 return? Okay, so we have some people replying in the chat. Okay, some people saying false, NA. All right, yeah, any applied to logical 0, and I think I put this in your homework. Any applied to a logical 0 ends up being false. Okay, and so we can see this. So here I got x being a length 0 logical vector. And if I say any on x, I get false. And we can see this is going to play a role here, because in here I have a vector that says false, false, false. And so any applied to just this vector by itself, false, 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 will evaluate to false. Okay. If this thing, any applied to the length 0 vector, evaluate to anything other than false, and I applied any on x and w together, if this had evaluated to true, then this thing would evaluate to true. But we don't want that. We need this to still remain false. Okay. And we can see that having any evaluate to false doesn't mess up anything else here, right? So u is true, true, true. Are any of the values true? Applied to u by itself? Yeah, that's true. Okay. And even if x evaluates to false, are any on false along with the u, which are all trues, how will that evaluate? That will still evaluate to true. So it's fine that x evaluates to false here, the length 0 thing. Okay. If it evaluated to anything else, if it evaluated to true here, then we would result in issues. Okay. Applying that logic in the opposite direction also works. So here we've got all logical 0. Is that true? Okay, all logical 0 is going to evaluate to true, because if the length 0 vector evaluated to false, then all applied to this thing would end up with a different result. So right now, true, true, true by itself, and if I apply all to it, it evaluates to true. But if I were to combine this true, true, true with a false, then this would evaluate incorrectly. But as it is, all x, all onto the logical 0, evaluates to true. And so this thing still remains evaluated as true. Okay. Do I need to say anything else? Okay. Another way you can think of it, if it's hard, so hopefully this makes some logical sense. There's some reason for why any logical 0 evaluates to false and all logical 0 evaluates to true. But if it's easier, you can just kind of just say, well, this is just the rules. So any takes on the default value of false unless one of the values is true, then it becomes true. All takes on the default values of true unless one of the values is false, and then it becomes false. We've got these comparison operators. Comparison operators allow us to kind of compare numeric values, and then it will return a true false statement. So we can just say is 3 equal to 3? You know, we test for equality. Is x equal to y? They are vectorized. They perform recycling. So if you have a vector of length, you know, x is a vector of some length and y is another vector of another length. It will do element-wise comparisons. And if one is shorter than the other, it will recycle the shorter vector so that they line up. So you've got test for equality, test for unequal, not equal to, you got less than, greater than, less than or equal to, greater than or equal to. And then you also have to see if one element is a subset of the other, or is an element contained in the other element. Okay, is X an element inside Y? Okay, so it's hard to, sometimes it's a little confusing, but you can still do less than and test for inequalities for strings and characters. And this is based on alphabetical order. So over here, I've got just numeric comparison. Is 10 less than 2? That's going to be false. 10 less than 2. But if you put something in quotes, then it does it's testing for kind of an alphabetical order, where things earlier in the alphabet have a, you know, less than sign as things later, right? So A comes before B, comes before C, comes before D. And that's kind of how we do the alphabet. Okay, and so the alphabet lowercase comes before the capital letter. So lowercase a comes before capital A, but capital A comes before lowercase b, and lowercase b comes before capital C, capital B, and so on and so forth. And so this is just alphabetical order, but the digits are also in alphabetical order. So you get a few kind of quirks that maybe we're accustomed to saying somewhat, but also maybe not. So for example, 1, 0, if we were to alphabetize them, 1, 0 comes before the character 2. Does that make sense? Because 1, as far as the character goes, comes before 2. And so this is kind of, it's just treating this as if this were like letters. And so rather than looking at the actual numeric value. So, so that's what we have here, okay? And technically, all of these symbols have an order as well. This is just some arbitrary order that the people decided. There's no rhyme or reason to it. There's no reason why the $ should come before the @ sign, or the question mark comes before the underscore or anything like that. This is just, if you were to alphabetize based on the symbols, this is what you get. But again, I mean, you probably shouldn't be alphabetizing on the symbols, but if you did, this is the result that you would get, okay? Then again, if you think about it, why is the alphabet in the order that it is? There's no real logic or reason to it. It just is, and we've accepted it, right? And we drilled it into your head and we said, this is the order, A, B, C, D, E, and you must remember it. And everybody's remembered it, and we have songs to help you remember it. And but that's just the order that somebody determined, and that's it. Oh, excuse me. Yawning in your own class that you're teaching is not a good sign for the students, but I've given you one quiz answer, right? Let's go ahead and give you your second answer. Your second answer today is E. E as an elephant. E as an elephant. All right, we got these functions. They're all is functions. And basically, you apply any of these functions and they're going to return a logical value, right? So is it missing? True or false? Is it null? True or false? Is it a double? True or false? Is it an array? True or false? Okay. And they can be used inside a conditional. All right, so let's talk about conditional statements. Conditional statements are basically these if statements. If this condition, then do this, right? If this. And so the condition that goes inside the if statement, it has to be logical. It has to be a kind of a logical true or false value, and it cannot be missing. It cannot be missing. It cannot be NA, right? And it needs to be a length 1 thing. Okay. If you give it a condition with a length greater than 1, R will accept it, but it's going to give you a warning. It's going to say, hey, you gave me multiple things here. I'm just going to take the first answer. Okay. If you give it something that's not logical, it's going to coerce it to logical. All right. It's not going to complain. It'll just coerce it to logical. If this condition is missing, NA, you're going to get this error. Missing value where true, false needed. This is a very common error. This is one where you should kind of memorize this error, and you'll know that this happens when you have a missing value in NA inside the condition. And if the condition ends up being length 0, you're going to get a different error. You're going to get argument is of length 0. After the condition, you use curly braces to kind of group the expressions that are going to get evaluated if the condition is true, right? So, simple example, X is this vector 1, 3. The conditional statement, the conditional operator is the in. We're going to say is 1 an element inside X? That returns true. Okay, it's a length 1 logical vector. And so I can put this condition, if 1 is an element in X, print hello. And indeed, it prints hello. Here, I'm going to, X is still this vector containing 1 and 3. And I'm going to say, is X greater than or equal to 2? All right. This is a comparison operator. It is vectorized. And so it's going to do element-wise comparisons. And it's going to say, well, 1 is not greater than 2. So that's false, greater than or equal to 2. But 3 is greater than or equal to 2. So that's true. So this statement, so this is a logical vector of length 2, first element false. So we're going to say if, and inside here we got false true. If false true, then print hello again. And so it sees this length 2 vector. It's going to say, you know what? I'm only going to look at the first value. The first value is false. The first value is false. And because it's false, it is not going to execute this code. All right. But it also says, hey, you gave me length 2, and I don't like that. So it gives us a warning, right? It says, when I have if statements, I don't like vectors greater than 2, right? It says the condition has a length greater than 1, and I'm only going to use the first element. So it gives us a warning, right? That's nice of R to give us this warning. And so then we say, well, is this really what I wanted to do? Oh yeah, maybe it is, maybe it's not. Over here, I do the same thing. I just do is X less than or equal to 2. It's true, false. And so this time, because this is true, it gives me the same warning because it's a length greater than 1. But because it is true, it does execute that code. And it says, say, print hello again. And it prints hello again. Yay. One thing you can do if you have these vectors that are length greater than 1, then if we length greater than 1, you can throw it inside a vector like, or inside a function like any or all, which will take, the logical vector length greater than 1, and it will ask, are any of the elements true, or are all of the elements true, or something. And so you can apply that, and then you can run it in here, and it will execute the code. No warning here because this statement is this length 1 vector. If you so if you remember our lecture on subsetting, and you subset an atomic vector to an index position that doesn't exist, what is the result? This is going to result in NA, right? So X is a vector 1, 2, 3, and I say, what's the 5th element in X? That's going to be a missing value. So X square bracket 5 is an NA, and we say is NA greater than or equal to 2? that's going to be a missing value. So here, basically, I have if NA, okay? If NA will always result in an error. It will say missing value or true, false needed. Because it doesn't, the decision to execute this code or not execute this code is a decision that depends on what is in this value, right? If it's true, you must execute this code. If it's false, you must not execute this code. And the decision to either execute this code or not depends on what's in here, and we just don't have the answer. So what are we supposed to do, right? What are we supposed to do? And so, so we don't know, right? It's kind of just like, yeah, should you order tickets for your friend? Well, it depends on whether your friend is going to say yes or no, right? You don't want to spend $100 if your friend's going to be a no, but if your friend's going to be a yes, you want to buy it. But until you get that answer, don't pull, don't make a decision. And so we need an answer. We need an answer, okay? And that's why a missing value is going to give us an error, okay? And so this, again, memorize this error. A lot of times when you're first starting coding in R and you get these errors and you read something and you go, well, I don't even know what I'm supposed to do with this, okay? Well, some of these errors you can, they tell you, they give you information about what you're supposed to do. So this missing value or true, false needed, it tells you the exact statement that caused this problem. And here it's if x square bracket 5 is greater than or equal to 2, we can find it and we can say, oh, you know what? This is the only thing that is a variable here. And we know that this thing has to be missing, and let's figure out why. Oh, it's missing because I'm asking for the 5th element and x is only length 3. That's why. Here, if we have a logical 0, we're also getting an error. Okay, so here x is this vector 1, 2, 3, and we can say which elements of x is equal to 4, right? Well, none of the elements in x are equal to 4. And so the answer here is integer 0. There's no integer index that's equal to, that will give us x equal to 4. So this is integer 0. And so if you do integer 0, this is basically asking, is the result of this question equal to 4? And that's going to be a logical 0, right? So here, I think I did this right. So x 3, and so here's x. I can say which x is equal to 4. That's not an answer, right? And I can say which x is that basically is integer 0. Is integer 0 equal to 4? That's going to be a logical, right? So when you compare something using the equal statement, the result's going to be logical. And the answer here is a logical vector of length 0. And basically, if you do any kind of statement with it, if logical 0, doesn't even matter what's inside here, you get an error. Error argument is of length 0. Okay. Likewise, if you do anything with an NA, with NA, you're going to get a missing word true, false needed. Okay. So here we're getting argument of length 0. It doesn't like this if statement. Our conditionals, we can nest them. We can say, if this is the thing, do this. And if that's not the thing, check another thing. And so on and so forth. Hold on, we got a question. It says, why does integer 0 equal 4 return logical 0 instead of false? Well, it's a 0 length vector, right? It's kind of just like, is null equal to 4? It doesn't exist. It doesn't exist, right? So it's or like NA equal to 4, that's a missing value. And if you have a 0 length vector, okay, so integer 0 is basically nothing, right? Nothing that's supposed to be a number, right? So it's like I tell you, write down a number on this piece of paper, okay? But then you don't turn in the paper. So I have nothing. And then I'm asking, well, is it equal to 4? Well, the answer is, well, the answers should be yes or no, but I don't even have the paper to begin with, right? I don't have a number, right? So integer 0 is integer 0. And so if we try to do any kind of test with it, is it equal to 4? Well, the answer is going to be, it should be yes or no, but I don't even have anything. So I can't even say yes or no, right? It's different from saying, I have something and it's not equal to 4, or I have something and it is equal to 4. We don't want to say false, because false implies that I do have something and it's not equal to 4. Here I want to say I don't even have anything. I don't know if that helps answer your question. Okay, we don't even have anything, so we can't test to see if it's equal to 4. All right, so over here we're going back to these conditional statements, and we can say, well, if this isn't true, I wanted to check something else. Okay, and so here we've got the else if, right? So if we can say, if x is less than 0, tell me the number is negative, and if it's greater than 0, okay, if it's not less than 0, then check to see if it's greater than 0, and if it is, then say it's positive, and if that's also not the case, then it has to be 0. Okay, and so here I got x is 3. This evaluates false, so we're not going to run this code. And because this is false, we check the next thing. We got else, and so here we check this. This ends up being true, and so we're going to print this statement out. And we print out positive. Okay, so here I've got x is 0. This is false. We don't run this code. This is false. We don't run this code. And therefore, we have to run this code, the last thing. So this is going to be true, and it prints out 0. Okay, there's no conditional. Just this is what happens if everything else evaluates to false. Now, the statements of else only get evaluated if the previous if statement is false. So here I wrote x is less than, x is equal to 3. We're assigning 3 to the value of x. And we're going to say if x is greater than 0, print positive. Okay, so as it evaluates, it's going to say, oh, this is true. It prints positive. And because this statement is true, it's going to skip everything else. It will never execute this else. It will not look at this else statement. And this line of code will never get evaluated, because this statement is never going to be true when this statement is false, right? It's only going to consider this when this thing evaluates to false. Okay, and so there's no situation where this thing is false, where x is less than or equal to 0, right? If this is false, but this thing ends up being true. So this line of code will never get evaluated, right? These statements only get evaluated if the previous statement is false. The else. Okay. One thing is that if statements are not vectorized. Okay, if statements can only look at one element at one thing, and evaluate if it's true or false then. And so, whereas the if else is vectorized, and sometimes you just want to kind of assign values, and so this kind of entire thing can be shortened to this, right? So if we're going to say n gets the value yes when x is equal to 5, and it's going to get the value no, else what? Otherwise, then this can be shortened to this if else. We've got a condition to test, is x equal to 5, and what is the result that we're going to return if it's true, and what is the result we're going to return if it's false. Okay, this thing is vectorized, so x can be a vector, and you can have a logical vector, and it's going to return a vector, values that are either yes or no or whatever, this thing or this thing, depending on what happens here. Okay, so let me just show you an example. Not yet. Getting ahead of myself. Okay, let's talk loops first, and then we'll revisit this if else business. Okay, loops, on the other hand, allow us to kind of repeat a chunk of code iteratively. So here, our simplest is the for loop, and you give it a vector, and very frequently we just say for x in 1:10, and this will be a vector 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And here we're going to say cat x squared. So, we evaluate it for the first element, we get 1, then we do 2 squared, then 3 squared, then 4 squared, and 5 squared, up through 10 squared. And that's it, and it does it through everything in the vector. Now here, when you do a for loop, you probably frequently do this in some kind of integer vector. And when you're in this integer vector, that's kind of what we expect. But it doesn't have to be an integer vector. It can be any kind of vector. And lists are vectors pretty much, right? You can think of lists as like a train vector. Okay. And so here I've got a list of length 3, and it's a train containing a vector 1, 2, 3 in the first car, A through G in the second car, and true, false. Okay. And we can have it iterate over the list. And when you do that, it's going to go into each train car and pull out that element and operate on it. Okay. So here we can say for each element inside the train or in the list, print out the length of that object y. So we go for each object y in the list, print out the length y. So it goes to the first train car, it looks inside, and it says, oh, whatever's in there has a length of 3. Goes inside the second train car. What's in there? It's a vector of length 7. The length is 7. And what's the next thing? Vector of length 2. So it prints out 3, 7, and 2. And so we can run a for loop over any vector. In this case, it's a list. What is cat again? That's the question. Cat is like print, but more basic. So when you print out a vector, it will proceed, it will format things, and it will do like square bracket 1 and stuff. Cat just kind of outputs stuff onto the screen. I don't know. And so there's a few things that there's like separator arguments, and there's different arguments that go into cat, but cat just kind of raw outputs stuff onto the screen. There's a built-in set of values. One is the data sets, and inside there's state names, which has the list of all 50 states. And so we can say, what are the first 5 states alphabetically? And we get Alabama, Alaska, Arizona, Arkansas, California. And so now I've got a vector of length 5, and we can say for each element, each state in this vector of length 5, print out onto the screen, or cat onto the screen, the state. And for the first iteration, it's Alabama, then the next iteration, it's Alaska. And then combine that with character has. And then here we're going to say the number of characters in that name. And then this last statement, letters in its name. So now it says Alabama has 7 letters in its name. Alaska has 6 letters in its name, so on and so forth. Is state to keyword? There's no keyword. It's the same thing as for I in 1 through 10. Here it's for X in state name, or in this case, state in state name. So state is not a keyword. It's just something, so I know what I'm talking about. Okay, I could have just used I, K, J, X, Y, L. Back here I used for Y in this. Here it's just for something in this vector. Okay. When you run loops, big loops, and you have to store the results, there's a few good practices that I recommend, but again, this is not going to really make or break your code often unless you're dealing with some very big stuff. So here I'm going to say, we want to store the values, and we're going to go 1 through 10 million. And so here I create a vector of NAs length 10 million. Okay, I create a big vector, and then system time is a way for me to time how long this code takes to run on a computer. Okay, And, now I've got like this fast computer, right? And, but back in the day, this would have taken like a long time. And I say, I want you to square every number from 1 through 10 million. So whatever 10 million squared is 10 to the 14. And, give me all of these values and store it in results position X. Okay. And this takes me a little over 1/2 of a second to execute. All right, great. Another thing, this is not as great. This is a little bit slower, but it's okay. Here, I'm going to just say results 0, and we're going to store the result into position X, and we're going to do the X squared. It looks like the exact same thing. The only difference is that I started off with length 1. Here I started off and I said it's going to be length 10 million. Here it's length 1. And so every time I do this, I have to resize my vector, right? After my second iteration, I go, oh, you know what? I need to put this into a vector of length 2. Third iteration, oh, I need to make my vector length 3. Now I need to make my vector length 4. And so I have to resize the vector. So it takes a little bit longer, maybe 4 times longer. Okay, it's not the end of the world. This one is the slowest though, okay? Here I create an empty vector. And what I'm doing is I'm gonna take the current vector results, add on, combine it with the new thing, x squared, and store it back into results, okay? So I'm gonna take the results, add on this number, and store it back in results. Okay, add on a number, store back into results. And so here I'm only going up to 10 to the 5, 100,000, which is 1/100th of the work, but it is the slowest and it takes 13.64. That's like 5 times longer than this, okay? And even though it's only 1/100th of the work. And so, the true thing would probably be 500 times longer or something. So it's much, much slower. We don't want to do that. Okay. We have other kinds of loops. We got while loops, we got repeat loops. So while loops just keep running until the condition is no longer met. What's the question? How is it to avoid a loop by doing 1:10 through 7 times 1:10 through 7? I'm not sure if I understand your question. Oh. Yeah, okay, you can avoid the loop. You can just do 1:10 through 7 squared. Yes. Yeah, this is just a junk example, okay? Completely unnecessary to have a loop in the first place, okay? And these are just examples of showing what happens when you run a loop. Yeah, it's a lot of times if you can do a vectorized operation, it will be faster than a loop, okay? Not always, but most of the time, 99% of the time, a vectorized operation is going to be faster than a loop. All right, let me talk about these while loops. We're going to run out of time. Let me go ahead and give you your last view quiz answer for today. Today's last view quiz answer is B as in bear. B as in bear. If you don't know the length of the loop output, yeah, you're going to have to use one of the suboptimal loops, right? You're going to have to do this if you don't know the length of the output, and that's fine. Okay, it's not that big of a deal. Okay, and especially if your output is going to be length 100 or length 500, something under than 10 million, it's probably not going to make a big difference. It's fine. Just because I said this is a little bit slower doesn't mean you can't do it. Okay, if you know the length of the output, great. Set it up so you know how it's going to work. If you don't know the length of the output, yeah, you got to do this. Okay, that's all right. It's the cost of missing information. All right, while loops. It keeps running until it becomes false. So at I equals 10, it outputs 100 or it stores 100 into the 10th position. I becomes 11. At I becomes 11, this becomes false. And so the loop stops. And so when the code finishes, I takes on the value 11 and it output 10 and it like that. Okay, we got another loop. This is called a repeat loop. It's almost just like the while loop, except you put the condition somewhere else inside the code chunk. Okay, so you need to with a repeat loop, it's going to keep running until it encounters break. And probably you want to put break inside some kind of condition. And so you can do things more complicated. You know, the while loop is probably good enough for most situations. Sometimes you're like, oh, I need something weird going on, and so I have to do a repeat loop or whatever. But you know, this is just another option. Okay, it's going to keep running until it encounters break. So here it keeps going until I is at 10. It doesn't encounter this, so it stores 100. Then it becomes I becomes 11, and then at 11 this becomes true, and then it encounters the break and it exits. Okay. You got keywords break and next. So break quits the loop. So here I've got this thing. It says start at 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if it's even, if I divisible by 2 or mod 2 equals 0, which means it's an even number, then break. So it starts off at 1, then it reaches 2. It says, oh, 2 is divisible by 2. So let's break, and it quits entirely. The exact same code, all I'm going to do is replace break with the word next. Exact same code. I've just replaced break with the word next. What happens here? Well, rather than just quitting the loop entirely, it just skips to the next iteration. So it starts off at 1, it outputs 1. Goes to 2, it says, whoops, we're going to skip that. So it doesn't execute this code, so 2 doesn't get output. Then it goes to 3, and it says, okay, I'm not going to execute this code. This is false. So it outputs 3 to the screen. Then it goes to 4. This is true, so it skips. It goes to next, and it skips this line. And it goes, and now we just print out the odd numbers here. 1, 3, 5, 7, 9. Okay, let me just talk real fast here. Sequence length, sequence along, and stuff. Okay, a lot of times we'll just say, oh, here's some vector. I'm going to do 1 colon length L. And this works great for a lot of situations, right? You got some vector, L is a vector of length 3. I can just say 1 colon 3 or 1 colon length L, and this will produce 1, 2, 3. I do sequence along L and I get 1, 2, 3, or sequence length of length 3 and I get 1, 2, 3. Okay, this seems fine. And a lot of times we'll just write, we'll be lazy and we will write 1 colon length L. And this works 99, I don't know, most of the time. However, when will this break? It breaks if L has a length of 0. Because what happens if L has a length of 0? So if I create an empty list, which has a length of 0, and I do 1 colon length L, now this becomes 1 colon 0, and now I get this vector 1, 0. Okay. And when I try to run some kind of loop here, and I'm trying to subset length list L to the first element, this gives me an error. It says subscript out of bounds. Subscript out of bounds. I'm trying to get the first element in a 0 length list. And it says, you can't do that. You can't do that. Okay. So this results in an error. So the way we avoid this is if we do sequence along on a 0 length vector gives me a 0 length. Sequence along on a 0 length vector gives me a 0 length vector, 0 length integer vector. And so if I were to try to run the exact same code, this is the exact same code here, but now I've replaced 1 through length L with sequence along, nothing gets executed because it's a 0 length vector. So this is the recommended method, sequence along or sequence length L. These two things, nothing gets executed. Whereas 1 colon length L is short, convenient, and handy. It will result in errors if L is a length 0. Okay, your vectorizing code. Again, we have these if statements, right? If statements are not vectorized. And so if you wanted to do something, and so you're gonna, I apologize, we're out of time. You're gonna have to review these last few slides on your own. The if statements are not vectorized. And so here is a piecewise function, and I've just coded it using if statements. Okay, so I'm just saying if x is less than 0, then it's x to the negative x cubed. If x is between 0 and 1, then it's x squared. And if x is greater than 1, it's the square root of x. Okay, that's fine. This function is correct. But when you try to treat it like a vectorized function, it runs into problems because only the first element gets used in an if statement. Okay, so it's only going to look at the first value, which is -2. It only does this. So if you want to run it for a longer thing, you have to like put it into a loop. Okay, and loops are just a little bit less efficient. They're not vectorized. And so you can do it and you can say, I want to subset X to the ith element. And we're going to apply the function to the ith element, and we're going to store it into this vector plot values into the ith position. And it will run through each element one at a time, and it will calculate the thing, and we get the result that we want. We can vectorize it using ifelse. Okay, with ifelse is vectorized, and basically we can kind of set up our thing, and we can have the condition if x is less than or equal to 0, then do -x cubed. Otherwise, check to see if x is less than or equal to 1 and give me x squared. And if that's not true, then it's square root of x. All right. And so vectorized in one line, it looks like this. And I'm sorry, I know I'm over time. If you need to go, you can go. I'm just going to talk real fast here. And then again, please review these notes on your own time. So we can run this, and this time I can just run the entire vector x through the function. Okay, I don't need to use a loop. I can just run the entire vector x into the function, gives me the values, and I can plot it. It does give me a warning about NAs, and I've explained why it does that. Okay, so we will end here for now, and we'll see you guys on Wednesday. So this will be the end of today's lecture. And other than that, have a good day, and we will see you guys on Wednesday.